We're continuing our study of similar figures or in similar triangles. This is what we talked about last time. When we defined similar triangles last time, we said that all of the angles that are corresponding are congruent, meaning the same, and all of the sides are proportional, which means we can always set up for this the new divided by the old. Okay? That's what we're setting up today. We're going to have congruent corresponding angles, which means the same measurements, and we're going to have proportional side lengths. We also need to make sure we understand which ones are corresponding, which is what that bluket was about that you played at the beginning of class. So grab a highlighter and let's highlight some of the corresponding sides here. Okay, if we look, the side AB goes from no markings to one marking. So on the other triangle, going from no markings to one marking means that I would highlight XY the same color. Good morning. Can you sit in group 5? Can you sit in group 6? Okay. My next colored highlight would go from, let's go from one arc mark to two arc marks, which is B to C. On the other triangle, one arc mark to two arc marks is from Y to Z. Which means, last but not least, if I go from two arc marks to none, two arc marks to none, we now have our triangles highlighted, which means it'll be very easy to talk about the corresponding angles and the corresponding sides. This is what I believe your bluket was about. So if we look at the first problem here, A, B, C, and D, it says side length AB corresponds to, so red goes to red. So we say XY. Check, good. We remember this? Okay, the next one says XZ. So from X to Z, that's green, corresponds to AC, the other green one. Do we understand? This part says angle Y. Angle Y has one arc mark. So angle B has one arc mark. They are corresponding. They're congruent. Angle C has two arc marks. Angle Z has two arc marks. They're corresponding. Sound good? Fabulous. Okay, that's a review of what we did last class and what you did on your bluket. Today, we're learning about 3 similarity theorems. So these are theorems that are going to allow us to decide if triangles are similar. The first similarity theorem is called the angle-angle similarity. Angle-angle similarity. It's called AA, angle-angle, because you need two angles. It says if two corresponding angles are congruent, then the triangles are similar. So if we notice in this image, it's kind of small, so you got to zoom your eyeballs in here. We have angle A with one arc mark and angle D with one arc mark, which means that they are congruent. We have angle B with two arc marks and angle E with two arc marks, which means they're congruent. Since I have two pairs of congruent angles, that means that these triangles are similar. That's all it takes to be able to say, yes, they are similar, is two corresponding angles being congruent. That's the whole theorem. So let's check this in practice. Obviously, number 2 is done for you. If you see what Miss Caldera did with her notes, she said, if we look at this image, angle A and angle D were marked as 75 degrees. That's one pair of congruent angles. Then we noticed that angle C and angle F had two arc marks. So even though only angle F was marked as 31 degrees, what does that mean we know angle C is? 31 degrees. If I have two angles that are the same, that are corresponding, that's when I can immediately go down here and say, yes, these are similar because I have those two angles that are the same. Boom, done. Make sense? Once you have two that are marked the same, you're good to go. Can we try one together? In problem 3, remember we are looking for two angles to be the same so that we can write our similarity statement. The image starts off like this, but I've redrawn, or Miss Caldera has redrawn, the image for you. Do you see how there's this little triangle, AEB? And then the bigger triangle, ADC. What angle do they have in common? What letter did I say in both triangles? A. So if they both have angle A, that's the same angle. So they're going to be the same measurement. The other piece of information I'm given is that angle B is 52 degrees and angle C is 52 degrees. So when I separate these triangles to look at them both, I have the small triangle with angle A and 52 degrees, and I have that bigger triangle with angle A and 52 degrees. What does that mean for us? Are these similar? Yes, we would say yes, triangle AEB is similar, squiggly line, to triangle ADC by the angle-angle similarity theorem because angle A is congruent to angle A and angle B is congruent to angle C. So this part right here says similar. That's answering the question. Yes, they're similar by the theorem we're using, which is angle-angle, because I identified two corresponding congruent angles, and then I just gave my evidence underneath. That's the angle-angle similarity theorem. How do we feel about it? Can we identify two angles? Yes. Fabulous. Let's go on to the next one. The next theorem is called side-side-side similarity. In side-side-side similarity, I am now looking at sides. And since it's called SSS or side-side-side, how many sides do I need to look at? 3. Side, side, and side. Basically, you have to make sure all of the sides are the same. All right? So if all 3 corresponding sides are proportional, which, reminder, proportional means that we're going to do new divided by old, then we can say that they're the same. Let's highlight our example here so we can see what's happening. AB is going to correspond to RS. So I have AB divided by RS. I have BC over ST because these are corresponding sides. I have CA over TR because those are corresponding sides. You are setting up a triple proportion here. If you do this triple proportion and you find all of these numbers either in fraction form or in decimal form, and they're all 3 the same exact number, meaning this number does equal this number and the blue number does equal the green number, if those are true and they're all equal, you can say that they're similar by side, side, side. Let's view an example. In example 5, it asks me to determine if the following are similar by side, 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 and then write a similarity statement. So again, the color coding is going to be super helpful. We'll go TU as red and QR as red. So I have my red sides. We'll go SU and PR as my blue sides. Then I have TS and QP as my green sides. In the next little bit of this problem, where did I get all of these numbers from? After I put the letters in the fractions, where did I get these numbers? Good morning, can you sit in group 6? Any idea where the 10 came from? Yeah, from TU, the big triangle, the new one is 10, so I put the 10 up there. The 5 is the number on the red side, so I put the 5 here. Do we see that? So the blue numbers go where the blue letters were, and the green numbers go where the green numbers were. At this point, you just need to actually calculate those fractions. 10 divided by 5 is 2. 8 divided by 4 is 2. 6 divided by 3 is 2. Are all of these numbers the same? Yes. If all of these numbers are the same, we write the similarity statement, yes, the triangles are similar by side, 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 because all three sides are proportional. Make sense? Okay. Now the only way this can get more difficult is if I don't give you images at first, I give you side lengths. But we are really good at drawing triangles and labeling them correctly, and that's the only thing that's different from problem 5 to problem 6. In problem 6, instead of giving you the image, I gave you a list of the values. So what Ms. Caldera did is she took all of these numbers, RS being equal to 12, and she just popped them on the sides. ST is 15, TR is 24, 28, 35, 56. She set up the red fraction, the blue fraction, the green fraction, and then divided all of these numbers over and over again until we saw that these are the exact same fraction. If you don't like using fractions, by the way, you can go ahead and change these to decimals. These decimals would be 2.3 repeated, 2.3 repeated, and 2.3 repeated. Either way, in fraction or decimal form, do you notice that all three of these things are the same number? If they're all the same number, then we can write the following similarity statement. We can say that yes, triangle RST is similar to triangle XYZ because all three sides are proportional. So you're writing me a little sentence answer today, telling me yes or no, and then telling me why. These are similar by side, side, side. So we've covered angle, angle. We've covered side, side, side. On the back, there is one more similarity theorem that we're going to be able to use. The one on the back is called, I'm hovering because I still see people writing. The one on the back is called the side angle side similarity, which means we're going to have to look at both sides and an included angle in that order. Side, angle in the middle, side. If the two corresponding sides are proportional and the included angle is, congruent, then they're going to be okay by side, angle, side. Meaning, we look at side XZ and MP. We look at side XY and MN, which would be your blues and your reds. Those are my sides. I also look at the angle tucked in between them. So if you notice, in between the two colors I've colored so far, I have angle X and I have angle M. If these three things occur, that X and M, the ones in the middle, are the same numbers, and the side lengths are proportional, just 2 this time, not 3, just 2, then we can say that everything is similar by side, angle, side. Why is this not sticking today? So let's look at an example. It says, determine if the following are similar by side, angle, side. If yes, write a similarity statement. Okay, so what Ms. Caldera did is she said, all right, I'm going to look at this and I'm going to highlight NP and KL, the corresponding sides, and I'm going to make them a fraction. I'm looking at the sides that have numbers, essentially. I also have numbers on NM and KJ. So here's NM and here's KJ. Let's check their proportion. If we put the numbers for NP, which is 15, over KL, which is 20, and the number for NM, which is 6, over the number for KJ, which is 8, and I actually divide those fractions, are these numbers the same? Yes. Okay, so we're good so far. The only other thing we check is to make sure that these two angles are the same. Is K the same as N? Look at what's marked there. It's kind of hard to see. You have one arc mark on K. How many arc marks do you have on N? One. So are they the same? Yes. So since we see that the included angle is the same, we say, yes, the triangles are similar by side angle side because these two sides are proportional, which we just proved here, and the angle that's included is congruent. Let's do one together. Number 8. We're going to try to check if this is side angle side. This problem is kind of complicated because the triangles overlap a little. So let's make them look different, okay? Let's draw the small triangle and list out all of its stuff, all of its measurements that we know. So it's called AED. Do we see what I'm doing here? What number should I put on AE? What number is between A and E? 12. What number should I put on AD? 15. Okay, then we draw our bigger triangle. My bigger triangle is called ACB. What number should I put between A and C? 21, very good. And what number should I put between A and B? 25. Okay, so we have these two angles. We're going to check and see if we can prove that they're similar by the side angle side theorem. Let's highlight our sides here. We'll do AE in the red color and AC in the red color because those are on the same side of the overlapping image. AD will be my blue and AB will be my blue. Thank you, Miss B. Let's check to see if these sides are proportional. How do I set up my fractions? What should go on top? Let's do reds first. What should go on top of the red one? 21, the AC. I'm going to use letters first, but yes, we will use 21 in a second, which means on the bottom would be AE. We're going to check and see if that is equal to the blue versions, which would be AB over AD. Now what Brian said is right. When we translate these from letters to numbers, that means I'm going to have 21 divided by 12, and we're going to check and see if that's equal to, what is AB? 25 divided by 15. Calculator moment for me. Can somebody do 21 divided by 12 and somebody else do 25 divided by 15? You're going to get a decimal and that's okay. Just round it to 2 decimal places. Yeah, 1.67 and then I got 1.75. Are those numbers the same? No. If they're not the same, then we cannot use this theorem to prove that the triangles are similar, even though they have that shared angle. So even though they have the angles being congruent, we would have to say, no, triangle ADE is not congruent or not similar to triangle ABC because the sides are not proportional. By the way, this is saying not similar. So sometimes you'll have to say no, even though you're using the correct information to prove it. Those fractions have to be the same numbers whenever you change them to decimal form. All right, let's check out number 9. Number 9 is really, really interesting. And again, we're just going to highlight some stuff because it's obviously worked for you. The first part here says find the value of x. I see that x is here and x is here. So I know that this one's going to require some work to be able to figure out what the value of x is. We always start by figuring out what sides are similar. We'll go JL and PR to follow Ms. Caldera's work. We'll go JK and QP, PQ, and then KL, QR. If I fill in those values, just like we did before, in all three sides, I only have to choose two of the sides to solve for. Try to pick one that has full numbers and then one that has an x. Don't pick the one that has double x's because you're making your life doing the algebra more difficult. Just pick ones like the red and the blue here, where the red has an x and the blue does not. And when I write it just like this is cross multiply and divide. We've done this problem before last time. We cross multiply and then solve for x. Ms. Caldera showed you both the inverse operations method and the box method to solve this. So you can take your pick there to solve for x. Hooray, we found x. But this problem actually goes on to not just say solve for x like we did last time, but to also find the perimeter of that triangle PQR. So what Ms. Caldera did is she took that value of 4 that we found and she plugged it in right there. 4 plus 2 means that this green length is 6. So perimeter is just adding up all the sides. We would do 6 plus 8 plus 10. When she did 6 plus 8 plus 10 over here, she got the perimeter is 24 units. Check good? Fabulous. The last problem is really pretty cool. I love problems like this. When I teach my dual credit and my AP pre-calc classes, we do problems like this as well. So this is a cool problem. This is a very SAT style problem. So my juniors who take it in a few weeks, this would be great. It says that this person is standing 1.65 meters tall. That's how tall he is. At 2 p.m. measures the length of a tree's shadow, 28.05, stands a certain distance away from the tree so that the tip of his shadow meets the tip of the tree's shadow. This is what's happening in the picture. It says to find the height of the tree to the nearest hundredth of a meter. This image is confusing to look at because we again have two overlapping triangles. We have the triangle of the guy and we have the triangle of the tree. Let's separate them so we can see two separate triangles. My first triangle will be for the guy. How tall is this guy? 1.65. Cool. I'm going to make that look like a height. How far away, what is this value here, this bottom value? We're looking for, let me do this. We got this one. What is this distance here? Because I want to fill in this triangle. Say again? Well, 23.5 is this one. If all of this is 28.05 and this much is 23.5, how much is this? We'd find this by doing 28.05 minus 23.5 to find that missing length, which fast forward would be 4.55. So I put 4.55 right here. There's my small triangle. Let's do my big triangle. This is the tree's triangle. What is this measurement for the tree? Big triangle. $28.05 meters. And we're looking for the height of the tree. I'm going to put an H right here to represent height. It's like an X, but since it's height, I'm going to make it H. Okay, I have these values for both the small triangle and the big triangle. So we can set up a proportion. We would set up, using the colors this time, the new divided by the old equal to the new divided by the old. This is now an easy proportion for us to solve. Last class when we were solving these proportions, what did we do to solve? Cross multiply. Okay, so in your calculators, please, can someone do 28.05 times 1.65? Trusting you can type this in a calculator later since no one calculated it for me. Come on. We get 46.2825. If I multiply the other direction, I get 4.55 times h. What do I have to do with these numbers to get that h, the height of the tree, by itself? Divide, very good. So we're going to divide both sides by 4.55, which again is an ugly decimal for us, but we find out that the height of the tree is going to be equal to approximately 10.17 meters, which is actually a really, really tall tree. It's like 30 feet tall, approximately.